Subscribe now.
So in the double sideband modulators, just as we did for general modulation, right? The double sideband modulators also have its own way of generating it. We are going to talk about all of them. So for this one, we have two types. We have two types of DSB-SC. The first one is the balanced modulator. And then the next one is the ring modulator. We will talk about the balance modulator, and then for the ring modulator, we will just talk a little bit about it and then move on to the next one. So let's look at the balance modulator. So for the balance modulator, what we want to achieve is that at the end of the day, we should come out with a modulated signal with the two sidebands, of which we suppress the carrier, as you can see, DSB-SC. So in general term, I would say that if you are doing DSB-SC, when we were explaining double sideband suppressed carrier, we multiplied the message signal and the carrier signal. So in this case, I can say that the double sideband suppressed carrier is a product modulator. The modulator that we are passing it through is a product PM modulator. But for the balance modulator, we arrange two AM modulators in such a way that at the end of the day, when we sum their resultant output, we are going to get the modulators or the modulator signal of which the carrier has been suppressed. So this is the general block diagram for a balanced modulator. So as you can see, the first one will be like, let me write here, this AM modulator, and then we have one oscillator inside. Let's say we have one oscillator inside. So this one we call it local oscillator. This oscillator is the one that will produce the carrier frequency wave for us. So we call it local oscillator. Anytime that you see local oscillator, that means that that's the source of the carrier frequency wave, right? So now this is one of my AM wave modulator. This is another one of my AM modulator. It's not coming. So with this, you assume that this is the center point. This is my source of my carrier frequency wave. So this is my message signal. So this being my message signal, M of t. And then this is also my message signal. But just that this is having a positive and this is also having a negative. And we use inverter to invert the original message signal into a negative aspect and then we place in. So the same source of frequency wave will be provided for all of them. So as you can see over here, this one is AC cos omega CT. This is my C of t. So in having this, I can say that the output of my first modulator will be x1 of t, let's say that way. And the second one output will be x2 of t. So at the end of the day, we'll be having a summer here with negative aspects and then with positive here. So the overall resultant here is going to be my modulated signal S of t. This is a block diagram for the balance modulator. So now let's look at how we'll be able to derive the general expression for it. So this is actually the block diagram for the balance DS. Let me do it. Here is a DSB-SC modulation. So here the resultant x of t is going to be equal to x1 of t minus x2 of t. That is it. So as you can see over here, the balance modulator is made up of two identical EM modulators. This is it, the modulator 1 and modulator 2, they are identical, and we have a local oscillator as well. These two are being arranged in such a way that it will superimpose their actual carrier wave, right? So in this way, it will kind of suppress it. And if it's able to suppress the carrier frequency, that's what we call balanced modulator. So now let's do some mathematical analysis for it. As I was saying, we arrange these two modulators in such a way that its arrangement was able to suppress the carrier signal, and therefore we were left with the various or the two sidebands. So let's assume that our S of t, right, our S of t is equal to AC into bracket 1 plus k, let's here k m of t, let's say cos omega ct. Based on this general AM equation, when you look at what we did over here, here is positive, here is negative. At the end of the day, when we do it, or when you are doing the general AM wave generation and it's positive, you are going to get the same thing as AC 1 plus k m of t cos omega ct. If we do it with the negative being attached to the message signal, after using the trigonometric identities, you are going to get a signal to be the resultant output to be AC into bracket 1 minus km of t cos omega ct. So this will be the two resultants output when the message signal is negative and when the message signal is positive. So now the resultant S of t, that means that the resultant output here is going to give me the first equation, and this one with the negative message. By using trigonometric identity, when you are doing the generation of a general AM wave, you are going to get the negative sign to be here, and therefore when you add them based on this sign from a block diagram, the S2 is negative and the next one is positive. So you are going to get AC into bracket 1 plus k m of t cos omega ct, which is S2 minus, let's say x1 minus S2, which is equal to S of t, and therefore minus AC into bracket 1 minus, let me clean this, 1 minus k m of t cos omega ct. So in doing this, you can see that when we expand whatever result that we are having here, we are going to get AC plus, let's say AC cos omega ct plus AC k m of t cos omega ct minus AC cos omega ct plus, because minus is plus, plus k m of t AC cos omega ct. So in this way, this one will cancel this one. The carrier band will be cancelled. That means we are suppressing the carrier. At the end of the day, we are going to get x of t to be equal to 2 AC k m of t cos omega ct. So this will be our resulting output after setting up our balance modulator to kind of modulate the signal. So now this is the resulting output. The general equation is the one over here that we are done deriving. But if you want to go further, you can just simplify. We are going to get 2 ACK AM cos omega MT cos omega ct. This is actually similar. These are just constants. These ones are the one that we derived in one of the tutorials. When we are suppressing the carrier, we derived in one of the tutorials. This is it. We used trigonometric identity over here to derive this. So these were constants and these were two trig identities, and we used those trig ratio identities to actually derive it, and we were able to come out with a final answer. So I am just doing this to show you that when you break this one down, you are going to arrive at two sidebands with lower sideband and upper sideband where the carrier has been suppressed. So in this way, we are going to arrive at the fact that this is our carrier signal which has been suppressed. The rest, we have our right sideband, which is the upper sideband, and then here it's our lower sideband with the frequency FC minus FM, and then FC plus FM. And then it also have its what? Amplitude, USB and LSB. And this is FC, which has been suppressed. So this is how we can actually use the balance modulator to generate a double sideband suppressed carrier signal, modulator signal. I would like us to talk a little bit about the ring modulator. The ring modulator is more or less uses diodes. Most of the times when they do the arrangement and configuration, it uses 4 diodes, and they are connected in the ring structure. And therefore, it has a name because it's being connected in a ring structure. It has a name, ring modulator. So if you want to know more about this ring modulator, you can hit me up in the comment section so that I can give you more materials on it to read. I would like to also let you know that the double sideband suppressed carrier is also called product modulator, as I explained to you earlier on, because when we were doing it, we were multiplying the message and then carrier, and therefore we can also call letters the product modulator. So thank you for watching, and see you in my next video.